Why do some non-polar substances have such high melting and boiling points? Why is iodine, I2, a solid at room temperature when it's non-polar? This comes down to the forces between the molecules called intermolecular forces. An iodine molecule and any other large non-polar molecule is going to have quite a high number of temporary dipoles in the molecules. Those temporary dipoles allow the two molecules to interact and form temporary dipole forces, which we call intermolecular bonds. So these are our intermolecular bonds. So what are these temporary dipoles? Well, when you have a molecule, even if it's non-polar, the electrons in its electron cloud are not always going to be evenly distributed. It's not going to be a homogeneous arrangement of electrons. At any instant in time, it is likely they'll be more densely packed on one side than on the other. And then an instant later, it'll be the other way around. This creates instantaneous dipoles. And the analogy I'd use is classrooms and students. If you're in a small classroom, the students in the class are pretty evenly distributed when you're sitting at your seats because there's only room for enough seats for the class. There's an even or homogeneous distribution of students, electrons. If we then opened up a sliding door between those two rooms or went into a more open learning space and let you sit where you want, you're likely to be less evenly distributed. So there's more seats available, more space available, so you're more likely to be unevenly distributed. There'll be one side of the classroom that probably has got more students than the other at any one instant. So you've got, even though it's the same number of students, you've got an uneven distribution. And that would be like a bigger electron cloud. The electrons have got more space to go in, so they're less likely to be distributed evenly. Move up to the theatre and let you sit wherever you want. It's almost certain there's going to be pockets of student electron density, and that's something like iodine, a really big electron cloud for a diatomic molecule, and the electrons sort of create these delta negative pockets where they're more to one side than the other. So that's an instantaneous dipole. It's determined by the size of the electron cloud, but we don't have that data quickly at hand. It's not something we can just look at a periodic table and go, oh, that's X times bigger. We'd actually need a list of atomic radii and make some inferences. So instead what we do is we use the molar mass as our guide, because the size of the electron cloud is proportional to the molar mass. The bigger the molar mass, the bigger the electron cloud. The bigger the electron cloud, the less even the distribution will be of electrons, so the more likely it is to have a temporary dipole, called an instantaneous dipole. So that's how dipoles are created, to allow forces to occur between neighbouring non-polar molecules. And the bigger the molar mass, the more likely this is to happen, which is why something like iodine is a solid. Whereas bromine, which is just above it in the periodic table, Br2, has a smaller electron cloud, so these forces don't happen as often. These dipole forces don't happen as often. They're not as strong because the instantaneous dipoles don't occur so often with a smaller electron cloud. So that's liquid at room temperature. Its boiling point is a bit higher than iodine's, although iodine's is sublimation, but that's a moot point at the moment. And chlorine and fluorine have got really tiny electron clouds compared to the other two. So the chance of them having instantaneous dipoles is much, much lower. That's why their boiling points are so low. The forces between the molecules are pretty much non-existent in those two, because they don't form instantaneous dipoles as readily, because they have a smaller electron cloud, and we can show that with their smaller molar mass. Now, when something with a dipole, whether it's instantaneous or permanent, so this can be a polar molecule as well, when it comes next to a non-polar molecule, the delta minus side is likely to repel electrons within this electron cloud. And what that does is it induces or creates a dipole in the neighboring molecule. So if the electrons are moved ever so slightly this way, this side becomes delta minus. And if this is delta minus, this side must be delta plus. So slight positive charge. Now you've got a slight negative and a slight positive next to each other. An intermolecular bond forms between them. And we name that, if it was this situation here with iodine and iodine, non-polar and non-polar, we would name that as a temporary dipole force. That is the specific name for the intermolecular bond that is formed. Now, if this was a polar molecule, let's say water, because iodine is slightly soluble in water. If this was water, which is a polar molecule, it has a permanent dipole. And so the name of this bond would change from temporary dipole to permanent dipole, temporary dipole. They're still intermolecular bonds, which you met last year, but now we're being more specific with the name. You need to say what type of dipole is attracting what type of dipole.